Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we're very happy to have Nikhil
Srivastav? Srivastav, yep.
Nikhil Srivastav from Yale, who is Dan Spielman's student, and he's going to be talking about some joint work with Dan. Many of us know Dan. And he's going to be talking about Twice-Ramanujan Sparsifiers.
Thank you. Okay, so this is joint work with Josh Batson and Dan Spielman, and Josh was an undergrad at Yale, but now he's a grad student at MIT. Okay, so let me start by defining the problem. So the objective of sparsification is to be able to approximate any given graph G by a sparse graph H for some useful or natural notion of approximation. So what we would like to happen is sort of shown in this picture here. You're given an undirected weighted graph G on n vertices on the left, and we would like to construct a graph H on the same set of vertices, which is sparse, so it has very few, say order n log n or order n edges. And we would like H to be close to G in some rigorous, well-defined sense. And we're going to allow the weights of edges in H to be different from each other and from their weights in G, as indicated by these thicker lines here.
Okay, the number of edges? About n?
About n, yeah.
About n.
Okay. So there are essentially two kinds of reasons why you'd want to prove this. I mean, one is just a really interesting just graph theory theorem to show that every graph is close to a sparse graph in whatever sense. And the other kind of motivation, which is more practical, is that H is a lot cheaper to store in memory and faster to compute with since it has less edges. So if it's close to G in some appropriate problem-specific sense, it can be used as a proxy for G in computations, and you can do things faster. Okay. So one of the first constructions of sparsifiers was given by Bengtler and Karger in 1996 for the purpose of finding cuts. And for them, a graph H approximates a graph G for every cut S, that is, for every subset of the vertices S. The total weight of edges leaving S is approximately equal in G and in H. Okay, so here on the left we have G, we have some cut S, has a whole bunch of edges. On the right we have the same cut, most of the edges are gone, but the weights on the remaining ones are blown up, so the total weight is within, say, 1 plus or minus epsilon. And if this holds for all cuts, then we say that H is a cut sparsifier for G. And what Bengtler and Karger showed is that for every parameter epsilon, every graph G has a cut sparsifier with n log n over epsilon squared edges. And you can find this in nearly linear time in the number of edges in G. So this was used to speed up all kinds of algorithms for any kind of cut optimization, like sparse cut, max cut, min cut, whatever. Because as far as cuts go, G and H are about the same thing, and H is a lot faster to compute with. Okay. So to talk about the notion of approximation that I'm going to show you in this work, I need to introduce a matrix associated with the graph, which is the graph Laplacian. So the Laplacian of a graph on n vertices is a symmetric n by n matrix L given by D minus A, where D is a diagonal matrix containing the degrees of the vertices, and A is the adjacency matrix, possibly weighted adjacency matrix if the edges have weights. And the Laplacian has this nice expansion as a sum of outer products over the edges. So it's a sum over ij, over edges ij, of the outer product delta I minus delta j transpose, where delta I is just a vector that has a 1 in position I. And this is weighted by, if the edges have weight Cij, this is weighted by Cij. Okay. So it's immediate. I mean, two basic.
Each one of those is like a vector with just 2 plus or minus
Yes.
1 entries in it?
Yeah. So this is a vector with a plus 1 in position I and a minus 1 in position j. So this whole thing is a matrix with 4 non-zero entries.
Wait, sorry, it's a little too quick for me. So the diagonal, the DG, you say it's the degree. What do you mean by degree? In degree, out degree, total?
It's an undirected graph.
Undirected, so
Undirected
just
graph. Just a total degree. Okay. Okay. So what we're really interested in this talk is a quadratic form of the Laplacian, which is defined as follows. So if x is a real function on the vertices, so it's a vector in Rn, the quadratic form x transpose Lx is simply the sum of differences squared, xi minus xj squared, over all the edges. Okay.
Well, that
Excuse me?
define.
What are
is the entries of the adjacent.
I'm sorry. The Cij are the weights of the edges
In AG.
in G. Yes. Okay. If the
Right,
graph is
defines the
weighted.
matrix. Yeah.
So this is immediate from this outer product expansion, and from it follow two basic facts which we're going to use. First is that the Laplacian is positive semi-definite, because this quadratic form is a sum of squares, it's always non-negative. And the other is that if the graph G is connected, then the kernel of the Laplacian is exactly the span of the ones vector, because for this sum to be 0, x needs to be constant across every edge, and if the graph is connected, this means it needs to be constant everywhere. Okay? So I'm mentioning this because L is a singular matrix, but we know exactly what its kernel is, and so in this talk, all the vectors I'm going to deal with are orthogonal to the ones vector. So I'm going to talk about L inverse in some places, and that's going to be totally okay, because I'm orthogonal to the null space. Okay. Okay. So having said that, I can get back to my cut sparsifiers and describe them in terms of the Laplacian. So it turns out if I take any cut S and I look at the characteristic vector of the cut, and I look at the quadratic form evaluated at the characteristic vector, this xs L xs transpose L xs, then I simply get the total weight of edges crossing the cut, because the only terms in the sum which are non-zero are those that have a 1 and a 0, so they correspond to an edge that has one endpoint inside S and one endpoint outside S. Okay? So in this language, what Bengtsson and Karger showed is that every graph G has a sparse, for every graph G there's a sparse graph H, for which the Laplacian quadratic forms are preserved up to a multiplicative 1 plus or minus epsilon factor for all 0, 1 vectors. Okay? This is what they showed. And what we show in this work is that you can construct graphs that satisfy this guarantee for all real vectors, which can be shown to be a strictly stronger notion, and we show how to do it with order n instead of n log n. Okay? So why would you want to do this? There are a few possible reasons. So the first is that the quadratic form of a matrix gives its eigenvalues. So by the Courant-Fisher theorem, if I preserve the quadratic form of G, I now have a sparse graph H which has all the eigenvalues in approximately the right places. So spectral graph theory relates these eigenvalues to some combinatorial properties of the graph. So H automatically inherits certain interesting properties of G.
Wait, but it's not true that they're equivalent for the spectral purpose in the sense of the eigenvalues. But
yes.
The eigenvectors may have not much to do with each other.
Right. This is an overly general statement. The extreme eigenvectors do, but the other eigenvectors, the eigenspaces, do not. They're related in some way, but definitely not. Okay. But the extreme eigenvectors, if you want to do spectral clustering or something, then you would get about the same thing if you ran it on G or on H. Okay. Okay. A few more things. Basically, you can encode a lot of information in this quadratic form. So it's a natural notion of energy on a graph. So if I look at the graph, identify the graph with an electrical circuit in which every edge is a unit resistor, then and I look at some potentials on the vertices, then the quadratic form is simply the energy that coming from the electrical flow that has those potentials. So it's well known that electrical flows are related to the behavior of random walks on the graph, like they determine the commute times, behavior of random spanning trees, the eigenvalues related to the mixing time, etc.
So does this give you better than the known estimates on mixing times then, for example? Or
no, not really. It gives you a sparse graph that would have the same spectral properties. Yeah, it doesn't actually.
Mixing
yeah,
time.
Similar mixing time. It wouldn't. Okay.
Well, so that actually, you could sort of try. You have this sparse graph and you could do a walk on it.
Mm-hmm.
Wouldn't then the equilibrium be similar on that to the one on the graph?
Yes, the equilibrium would be almost the same.
So it would give you, for example,
a faster way of computing
if I
the mixing
sample
time.
because
a faster way of
count, I can actually use that to do approximate count.
Yes. Yes, it would give you faster in that sense. I thought you meant it would give you better bounds.
Better estimate of the mixing time,
yeah.
but much faster.
Yeah, you could compute some things faster, but right,
Yeah,
wouldn't necessarily
good.
be better.
Okay, fine. Not better, but faster, which is very important in many situations.
Maybe it'd be helpful for me with this. What are things that are not preserved very well, like distances?
Distances are not preserved. Okay. So this preserves. You can write the effective resistance distance in terms of the quadratic form, if you know what that is. But shortest path distances are not preserved by this notion.
You could apply this to a clique, and then of course.
Yeah, you get an expander if you apply it to a clique.
And if you had a graph that was clustered into certain clusters,
yeah,
those clusters themselves wouldn't be preserved.
No.
So they were disjoint clusters, and you did this.
Oh, well,
disjoint?
you could do this
Yeah.
for spectral
They would be.
clustering.
They would
yeah.
be. They would be. Well, not
if they're
if they
disjoint.
were mostly disjoint.
Yeah, they would roughly be
They
preserved.
would be preserved.
Yeah.
But as he was saying, the clique would all of a sudden turn into
Yeah.
this sparse graph.
Yeah,
So
yeah.
distances are like
Right.
just
But the
wildly
clusters would
different.
more or less be preserved.
Yes, yes.
Because this is used.
Because
as
the
a
cuts are more or
cluster.
less preserved.
The cuts
Right.
are preserved.
I mean, they're-
right. This is used.
Yeah.
Right. The spectra is what's important.
So
for
how
spectral
does it, I
clusters.
mean, I could think of another approximation to the graph, which,
Mhm.
I mean, if you start with a dense graph, it
Mhm.
would be, it's Samarelli approximation, where you just
Okay.
sort of tell the groups, and
Hmm.
so that would allow you to describe the graph approximately, actually,
Very concisely.
very concisely. So how does that compare?
I mean, this gives you, I guess this gives you much finer information. That would give you, like, for large enough sets, there's some, you know, the total number of edges is about what it should be in a random graph, is what the Samarelli thing would say. Or, I mean, this would actually preserve the weighted degrees of all the vertices. I think it would just give a lot finer information.
Yes.
Then.
Apply that to large sets of vertices and ask questions about
Mhm.
pairwise connectivity.
Mhm.
And here you can ask questions about
Right.
singleton pairs.
And that like small cuts get totally clobbered in the Samarelli approximation, but in this
But here they don't.
they don't. Even like one edge would be okay. Okay, so there's that. One more reason is
Same expansion.
yeah,
Because that's the
Yeah.
eigenvalue again. And
Yep.
he's got the eigenvalue.
they have the same cuts and the same
Same,
eigenvalue. Yep.
same
So-
eigenvalues.
Another reason to consider this notion is that it corresponds exactly to the relative condition number in linear algebra, which is a pretty basic, it's a straight notion of approximation for matrices. And it turns out, I mean, for this reason, that this is a key ingredient in the design of fast linear system solvers in a certain large class of matrices, like related to Laplacian matrices. So Spielman and Tang originally defined this notion of approximation for this purpose because they came up with this nearly linear time algorithm for solving linear equations, and this was used as a key step in like preconditioning those intermediate systems of equations that came up with that. So all I want you to take away from this is that this is like a reasonable notion, reasonable definition.
If you were to run this at like a social network,
Mm-hmm.
do you think you would sort of pull out the best friend structure?
What is the best friend structure?
You know, for each guy you have like one or two best friends.
I think you would pull out the sort of connectors,
Right.
the people. We can discuss this later.
Yeah, I guess it probably depends on how much. I mean, yeah, if there's somebody who's like a real bridge between two groups, then they would probably be preserved. But
Because that affects the conductance.
yeah, but
and-
otherwise, if somebody had a lot of best friends, okay, I don't know if that makes sense. But
No,
anyway.
I don't think it would
Uh-huh.
actually.
It's
Yeah.
terrible.
Don't,
Marriage
if
should
you
be
haven't met
destroyed.
Adam Collide, this is Adam Collide, and he makes statements like that all the time.
It's a reasonable.
Like, so I was an electrical engineer
Mhm.
one time, and what's X? What's the current? What's the voltage? What's the resistance?
Okay, so the edges are unit resistors.
Sorry?
The edges are unit resistors.
Okay.
You have this graph. You have some potentials on the vertices, and so the current flowing in every edge is like the potential difference.
Okay.
And so then they have
Like you have X transpose LX. So
Right.
What do I think of X?
Oh, that would just be the sum of the energy over all the edges. So the energy in a particular edge would be the current squared. Oh, what is x? X is the
This is the potential.
x transpose Lx is a number. X is the vector of potentials on the vertices.
Which is why it's really nice that you can do a general X and not just something which is zeros and ones, which represents the
Cut.
indicator function of a set. He can do a potential, and the previous work, they could just have X being zeros and ones, which would be the indicator function of a set. So he can do.
I think, I mean, if I understand you, I think you had to, so if you write this X transport Lx out, the contribution of the X, of the edge ij is xi minus xj
Right,
squared.
this thing.
And that would be times the resistance, so one of them would be the voltage, the other is the current, because you have the Cij, that's the energy.
So this is a potential difference squared. This is a conductance. So it's v squared over r, or whatever it is supposed to be.
Or I times B or
Yeah, like that kind of thing. Okay. Okay, so this is, I guess, some justification for why you want to study this. Okay, so let me show you some examples. You've probably seen under a different name. So the first one is, suppose the graph G I want to sparsify as a complete graph on n vertices. So it's well known that all the non-zero Laplacian eigenvalues of G are equal to n. Okay, and so it turns out that the best way to sparsify this is to take H to be an expander graph, and the strongest kind of expander graph you can get is called a deregular Ramanujan graph. So it's a deregular graph. It's a constant degree. D, think of D as a constant. And we know that all of its Laplacian eigenvalues are approximately equal to D. They're actually in the range D plus or minus 2 squared root D minus 1. So what that means is if I take this graph and I multiply the edge weights by n over D, so I blow up the weights on all the edges, I get something whose eigenvalues are about n. I mean, I'm being a little shady here, but it's approximately true. And so then, if I take this blown up expander graph and I compare the ratio of the quadratic forms, then this numerator is always something that's about equal to n. The denominator is always exactly equal to n, so this thing is about equal to 1. Okay? And so, what I want you to take away from this is that the correct approximations for the complete graph are expander graphs, and the best ones are these Ramanujan expander graphs. You could. That would be good too.
That is a Ramanujan graph.
Yeah, that would be with almost Ramanujan graph too. So, I guess, okay, I'm mentioning this because I should have written this quantity D plus or minus 2 squared D minus 1 because I'm going to compare what we construct to this actual bound later on. Anyway, the only slightly more complicated example is a dumbbell. Here you have two copies of the complete graph joined by a single edge. And you can approximate this by taking two copies of, or two expander graphs, with appropriately blown up weights joined by a single edge. And the reason this works is because this quadratic form is linear in the Laplacian. So the sum of the sparsifiers is like a sparsifier for the sum of the graphs. So the left half here is approximated by an expander, right half is approximated by an expander, and the edge by itself. Okay. So the two interesting features of this example, as opposed to the previous one, are the weights of the edges are radically different. So the weight in the middle is 1, and these are n over d, which is huge. And you can show that this is necessary. And any approximation you want for this graph, you'd better recognize this edge in the middle and keep it, because otherwise you disconnect the graph. Okay. Okay. So this is an example of an unweighted graph for which you can prove that any sparsifier must have edge weights, also, in case you were wondering. Okay, so what do we show in this work? So basically what we showed is we can do as well as what I showed you in the last two examples for any unweighted, for any weighted undirected graph G up to a factor of 2. Okay, so that's why it's called Twice-Ramanujan. Specifically, we have the following thing. So the statement that Ramanujan graphs exist is the statement that there are very sparse graphs that look like the complete graph. So they're degree D graphs for H, for which the Laplacian quadratic form of H is within a factor of D plus or minus 2 squared D minus 1 of the complete graph. Okay. So what we showed is that this is true for any graph G. So for any graph G, there's a very sparse graph that looks like G. And by look like, I mean exactly the same thing. This ratio of quadratic forms between D plus or minus 2 squared D minus 1. It should be less than or equal to. Now by very sparse, I mean average degree 2D. So I don't mean degree D. So this has twice as many edges. So, and it's not regular. And it's weighted. So the edges,
Wait, what is D now?
it's a constant, any parameter. So if you give me any D, I can get you an average degree 2D graph that satisfies.
Complete graph, you have recovered the maximum degree 2D?
No. For the case of the complete graph, like the combinatorial degree, it's not regular. I mean, we actually don't have very good control over what this does in the complete graph. So the graph that we produce, you need a weighted. In general, you need a weighted graph. I mean, for the complete graph, you don't need a weighted graph, but yeah.
No, but I'm saying that you have
Yeah.
examples
Yes,
where
we have
you
examples.
certainly know that you
Yeah, you need a weighted irregular graph. Yeah.
Wait, for the
which
complete
makes
graph,
sense.
you also need a weighted graph.
No.
Weight n over D.
Okay, that's true. Yeah, but same
Scale
weights,
it
all the
out.
same weights, all the same
Scale
weights.
it
That's
out.
true. Okay. So our graph that we produce is a weighted subgraph of G, which means that the edge set of H is a subset of the edge set of G, and it's weighted. It has average degree 2D, and we have a deterministic slow but polynomial time algorithm for constructing it. Okay.
And so the average degree is 2D. Do you have vertices which have degree n?
Yeah, you could. I mean, you're unlike. I mean, you could definitely have vertices that have degree that's a large function of n. I think yeah. In general, we don't have any control over it right
Know
now.
that that's necessary?
No.
So
We don't.
theoretically, there could be bounded degree and bounded degree.
I-
I mean, if the original graph has that structure, then it can be necessary. Are you saying for the complete graph? Or?
Right, but
Oh,
I mean,
okay.
that's the point. It can be necessary.
Oh, okay. Oh, you mean if it like contains a star or something?
Right. So you won't be able to, in general, get
Oh,
a
right.
degree graph out because
Right. I mean, you could have a star, and then cutting any of those would disconnect the graph or something. I think. Right. Well, that's what you said. Okay. Okay. So this is the result.
that's Adam's friendship.
It's a star. That sounds pretty good. The average degree of the star is like 1 or something.
Okay, good.
Okay. Okay. So here's a comparison of this to some previous works. So you can see this as some kind of generalization of this phenomenon of expander graphs. Since the algorithm is deterministic, you can see this as some kind of deterministic way to produce graphs with good spectral properties. I mean, they're weighted, but it improves the previous result with Dan Spielman from 2008, in which we showed you can do this with dn log n edges.
And now you have...
And now we have dn, like dn.
Oh, so you got rid of the log.
We got rid of the log. You can think of this as just getting rid of the log.
Oh, that's a lot. Yeah.
And it's optimal up to like factor of 4 or something like that. And it's also determined, I mean, all the previous algorithms for such approximations were randomized, if you care about that sort of thing. So it's deterministic. Okay. Do you have a question? Okay. Okay, cool.
So, in particular for expander construction, I mean, if you want n log n edges, it's not as interesting as...
Yeah. Right, yes.
Yeah. Yeah.
Okay. So I'll show you the proof of this theorem, which is very simple and can be fit in this talk, and it's just linear algebra. And for simplicity, I'll show you the case when G is unweighted, and I want to find a subgraph with 6n edges. So the quadratic form is approximated up to a factor of 13. Okay, it's some constant, but it's the same thing. Okay, so I'll start by reducing this to some clean problem in linear algebra, and then the rest will just be that. So recall that this is what I wanted to do. Given a graph G, I want to find a sparse subgraph H for which the quadratic form is approximated up to a 13. Okay? I'm going to rewrite this in a sort of different suggestive way. So recall that the Laplacian has this outer product expansion. It's a sum of outer products delta I match delta j, delta I match delta j, transpose over edges ij. Let me stop so I can stop saying that. Let me call these things BE and index them by the edges. Get sum of BE, BE transpose. Okay? So this is a nice property that if H is a weighted subgraph of G, then it has this expansion in terms of the same outer product. So some SCE, BE, BE transpose, where SE is just a weight of E and H. So if H is a sparse subgraph of G, then most of the SEs are going to be 0, and the rest of them will be whatever they're supposed, whatever they are. Okay. So with this in hand, I can start modifying this a little bit. So it's easy to see, just by multiplying by the inverse of G on the bottom and the top. This is equivalent to showing that there is a sparse graph H for which the matrix LG to the minus half, LH, LG to the minus 1 half has eigenvalues between 1 and 13. Okay. So I can open this thing in the middle in terms of these outer products. It's the same as saying there's a sparse set of scalars SE for which sum over edges of G, SE times whatever LG minus 1 half BE times its transpose has eigenvalues between 1 and 13. And now let me just call this vector VE. Yes? Oh, okay. So here LH is I can write LH as the sum of these outer products.
Can you go slower?
Sure. Okay. So I'm going to use this. Okay. So this is what I wanted to do. So I just multiplied by LG to the minus 1 half on the bottom and top, and so my goal is now to find a graph H with this property. Okay. On the previous slide, I showed you that if H is a weighted subgraph of G, then I can write it as the sum of outer products. That's all I'm doing in this step. So notice if I put a sum of outer products here, this thing is linear and whatever is going on here, so I can just take the sum outside. The sum of...
Or you just wrote
Yeah, I just wrote it. I just wrote it out.
LH is the sum of them, and
Okay.
of course the square roots just come right in.
And now, so I don't have to keep
and by
writing.
the way, it's not just, this would also just be an operator inequality, right? You could just say one smaller equal.
Yes, exactly. And so I don't have to keep writing this. I'm going to call this thing VE. Okay. So for every edge E in the graph, there's a vector VE, which is LG minus 1/2 B. Okay. So I just want to find some SEs. So sum of the outer product VE transpose weighted by SE is between 1 and 13. Eigenvalues between 1 and 13. Okay.
VEs are a function of just the original.
The VEs are a function of the original graph. Yes. So now I'm going to look a little more closely at the VEs and see what I know about them.
Let's see, what is, can you go, so this other SE is positive?
Yeah. Oh yes. I'm sorry. They have to be non-negative. Yes. They're supposed to be edge weights.
So the SEs are what you want to choose. They should be the weights on the edges.
Yes. So you want to choose a sparse set of SEs for which this thing
And
holds.
you have still written, so you have written this as a sum of positive operators.
Yes.
And if you had put in just ones instead of SE, you would have gotten 1 on both sides. This
Yes.
form would have been-
Right. Yeah. So if you take H equal to G, then all the SEs are 1, and you just get in the middle. You just get the identity. So everything is green. All the eigenvalues are equal. Okay. Okay. Okay, so let me take a closer look at the VEs. Okay, what are the VEs? If the graph G has m edges, then there are m vectors VE. They live in Rn minus 1, since they're all in the span of the Laplacian, assuming the graph is connected. And so my graph G is, it's m vectors in Rn minus 1. That's what I want to think of it as. And the only property of these things which I'm going to use, and the really crucial property...
Minus 1 because you divided out the constant vector.
Excuse me?
It's minus
Yes,
1
because I cut out I got rid of the span of the ones vector. Yes. So the only property of this that I'm going to use is that these vectors form a decomposition of the identity. So sum of outer products onto these vectors, sum VE transpose is equal to the identity. This is exactly what you said earlier about all the SEs being equal to 1. And this is simply because sum BE transpose is just equal to the Laplacian of G, and then I'm just multiplying it by its inverse, and I just get the identity. Okay. So you have a large number of vectors in Rn minus 1, and they add up to the identity. Okay. So the moment ellipsoid is the sphere. So if I look at any unit vector,
I mean, you can presumably find more than one VE for which would solve this or not.
which would
Is
solve
it a
this?
unique? Are you looking for a unique solution or not?
No.
Because
There could,
presumably
you mean
that's-
SEs, right? Yeah.
Right. That's not
Yeah.
much or SEs.
Yeah, I'm looking
I mean,
for
there's
any-
not much of this is not much of a constraint. It's
Right,
somewhat
yeah.
of a constraint,
Uh-huh,
but
but
it
yeah.
doesn't.
Mhm.
It doesn't uniquely.
No, it does not uniquely.
Determine
but,
the SEs.
sorry, alternately, just if I found SEs such that the sum of these outer products was
He's
the
happy.
identity,
Mhm.
then you'd be like done perfectly.
Yeah.
Yeah.
Even better than you could
Yes.
hope for. Okay.
I mean, that can be shown to be impossible, but yes. Okay. If I look at any unit vector U and I look at the sum of projections onto the V squared, I get 1. It's just saying that it looks the same in every direction. If you're more comfortable with this for whatever reason. So, okay. So having said this, let me go back to what I was doing. I wanted to choose a sparse subgraph H. This corresponds to choosing from my decomposition identity a small subset of vectors, possibly with stretching, so that the eigenvalues
With stretching meaning they're just
just
weighted.
they're
It's a
weighted.
weighted
It's a weighted, yes, possibly with these non-negative scalars SE,
Sure.
so that this new thing that I have has eigenvalues between 1 and 13, so that its moment ellipsoid is approximately a sphere. Okay.
Mm-hmm.
So all I've done so far is just transform this problem about graphs and Laplacian approximation into this problem about vectors. You're given some decomposition identity.
Mm-hmm.
You want to find some sparse weighted subset, which is approximately the identity.
Does every decomposition of the identity correspond to a graph G?
No. Okay. So in particular, I've shown that it's going to suffice to prove the following theorem. Given any decomposition identity in n dimensions, there's scalars, non-negative scalars, at most 6n of which are non-zero, for which this weighted sum of outer product has eigenvalues between 1 and 13. So in the actual thing, we can prove this with these parameters, that for any d, you can find at most dn non-zero, so that this thing is between d plus or minus square d minus 1, which gives you the result for graphs. But I'm just going to show you this in the talk.
Sure.
And that's it. So we're not going to talk about graphs, and I'm just going to prove this theorem.
Are you going to
Of 2 in the graph case, you got 2 D.
Right. Okay, so that's this thing where if you have d and edges, then your average degree is 2d.
Yeah.
So, so yeah.
Or what do we say about average degree here?
In this case?
How do we see where's the average degree hidden?
Okay. So each of these things corresponds to choosing an edge. So if at most dn are non-zero, then there are at most dn edges. So the average degree is twice the number of edges. I'm sorry, divided by n.
With your 13 or whatever. What
Oh, the average gear would be 12.
Is this related to stuff that people do when sort of when they study orthogonal frames and Hilbert spaces?
Yes, it's exactly that. That's exactly what it is.
Good.
Okay. Okay, so now I'll just give you some intuition for this proof before actually showing you the proof. So basically, I'm going to build this approximation in steps in an iterative process. I'm going to start at 0. At every step, I'm going to increment one of the scalars SE. That's going to correspond to adding a vector, like adding one of these outer products VEV transpose. And this is going to change the eigenvalues of what I have in some way. And I'm going to keep track of the eigenvalues. And I'm going to do this in a way so after 6n steps, my eigenvalues are between 1 and 13. Okay? And then by construction, there are most 6n that are non-zero, and you have the right property.
I see. So it's not that you increment an existing SE. You just work on each edge once and you get your SE right for that edge.
Actually, I should have, in every step you choose an SE to increment, actually. You may add an edge many, many times.
You may add an edge
Yes,
many
yes.
times.
I should make that clear.
So your
Okay.
degree may be,
So the degree may actually be a lot less than
Yeah, it may be.
Yeah.
The combinatorial degree may be less if you add every edge,
Right.
a whole
Good,
yeah.
good.
Okay.
Oh, is this the number of SEs different from 0? Or
Yeah, that's just
sum?
that's the number of SEs different from 0.
But isn't your degree weighted degree? Don't you?
Oh, okay. I'm sorry.
This is
Combinatorial degree.
my
I should be more clear about it. We're interested in having small number of non-zeros, so combinatorial degree.
I see.
The weighted degrees will all be exactly preserved because those are just cuts, or approximately, very closely preserved.
That was it, yeah.
Okay. So given that I'm going to try to do it this way, the basic question is, if I have a matrix and I add a rank 1 matrix to it, if I add one of these vectors, what happens to the eigenvalues? So this is a very well understood question. So if I have some matrix with some eigenvalues here on the real line, if I add VV transpose, then the eigenvalues move forward in a way that the new eigenvalues interlace the old eigenvalues. And this is sort of a well-known thing about rank 1 updates. So
What happens if they're degeneracies in
well, then the new eigenvalues remain stuck in the degeneracies.
I see. So it doesn't get any.
It doesn't change. Yeah, it doesn't really change anything.
wait, what happened to them? You said they're
They interlace.
They interlace the old one. So he's looking at, so the blue ones are his eigenvalues before he added the VB transpose. He's saying the eigenvalues of the spectrum of the new one interlace.
Yeah, like each.
And that's easy to prove.
Yeah, it's pretty easy to
Yeah.
prove.
should go down.
Oh, it should go up. Okay, I guess these are the dead old eigenvalues, and the blue things are the eigenvalues. So this is where everybody used to be before, and now everybody. I'm deliberately not giving names to the eigenvalues because they don't really have names, but you can think that this one moved here, this one moved here, and so on. But at some level that's not true. But yeah, they shift forward, so the new ones, Okay.
So if you had a little epsilon and you added this slowly, then the VV transpose are unit vectors or?
Any vector.
So if I add them in very little, then they are continuations. They would each of them just slowly moves to the next one, right?
Yes. If you kept going on, yes.
No.
No, but what he's saying, your V is like.
You're saying it's continuous
1
in
over
the
square
might
root
not
of
reach- it might not reach the
LG
next
times
It's continuous
times
in the normal
S, and if
V
you
on
were
it.
incrementing
S.
S really
Okay, continuously.
continuously,
Yeah, then this would move.
Then you could identify as what he's
Oh,
saying.
then you could identify. Yes.
And since there's no
Yes.
crossing by that happening,
the thing is that there could be the crossing is exactly the reason you don't want to do this. So suppose I add a multiple of this eigenvector only. Okay. Well, these guys are all going to remain fixed, and this thing is just going to move off to infinity.
so it will actually, there are crossings.
Right. Now, if you don't like crossings,
That's
then
not
you can
right.
think of it as this coming here, and then this going here, and then this going here, and so on. But, it depends on how you prefer to think about it. I'm going to discuss this in more detail. So, this is something that everybody, including me, always gets tripped up on, like which of these things is a better way to think of eigenvalues. But yeah. Okay. So I can get more delicate information about where these eigenvalues go by looking at what happens with the characteristic polynomial. So the characteristic polynomial of A is this, this polynomial, and
Wait, go back. Now you actually, I just thought about what you said.
yes,
So if we do this example, I choose the first eigenvector.
Yes.
What happens then? Then the blue ones.
well, then none of the other ones move because you're just adding something orthogonal to the first eigenvector, and this eigenvalue will just go off, like.
And how does that correspond to your pictures then? How do you have the interlacing then?
The first one went to the second one to the third.
Yeah. So yeah, the way you have the interlacing is you imagine that this went here. And, yeah.
I see. Okay. Oh,
I mean-
that's why you said we really should.
Yeah, we shouldn't give them names because the new set interlaces the old set. Okay. Okay. So we can look at the characteristic polynomial to get a better idea of exactly where these things go. And there's this basic lemma in linear algebra that tells you what happens to a determinant when you add a rank 1 matrix. So I can see what happens to the characteristic polynomial when I add a vector of VV transpose. Okay. So if PA is a characteristic polynomial of A, then the characteristic polynomial of A plus VV transpose is the characteristic polynomial of, maybe I should use this, of A, well maybe it's okay, times this quantity here. 1 plus the sum over I, where I are the eigenvalues of A, I are the dimensions, this ranges from 1 to n, times, this is the projection of the vector that I'm adding onto the ith eigenvector, divided by the ith eigenvalue minus x, okay? So it, yeah, this is a polynomial because this thing is a product of these things. So these are the eigenvalues of A, so these are the roots of PA. So I multiply PA by this quantity, I get a polynomial. Well, this is a product of lambda I minus x.
Right.
Over
so in each
from
of
I.
these it cancels out.
Yeah, it cancels one.
It just means that you cancel out the corresponding lambda
And
I
replace it with
minus
a
x,
projection.
Replace it by the projection.
Yes. And add that to the original polynomial.
Right,
Okay.
it kind of, yes, because you've got this product of factors. and
So
just cross
effectively
it out
you
and
add
it's
to your
denominator.
polynomial a polynomial of one lower degree in your,
Yes. Which depends on
and
the
which is
projection.
this polynomial
Okay.
value.
So
It's related to this Kramer rule of crossing things out, right?
yeah, actually, yes, it is exactly
all gotta be
related
the
to that.
same thing.
So okay.
And that
Yeah, it's the same thing. It's like
crossed
taking
out.
minors of a
The
matrix.
lambda I minus x is the thing you crossed out.
Yes.
That's true.
Okay.
You know that, right?
Even I know.
That's a really useful way of thinking about it, actually. So okay. So basically, the eigenvalues, the eigenvalues of A which didn't move are sort of going to be the zeros of this thing, and the new eigenvalues of A plus VV transpose are basically going to be the zeros of this quantity here.
Mm-hmm.
And this induces a simple physical model, which gives a lot of intuition for what actually happens with eigenvalues, which I'm going to describe. Okay, this thing in parentheses. So you have a matrix A in n dimensions. It has n eigenvalues. The eigenvalues are positive unit charges resting on an incline on a slope. Okay, so the slope is a real line. Okay, and the locations of these eigenvalues are, like whatever their values are. And each eigenvalue is a unit charge resting against this like massless, chargeless barrier. Okay, and there's gravity. So these things are sort of sitting snugly against these barriers. Okay, and they're not falling down the slope. Now here's what happens when I add a vector. If I add a vector v, then I add charges to the barriers.
So why don't they go up the hill?
I mean, this is sort of a hackish physical model. The charges don't repel each other; they only repel the barriers.
Okay.
So I mean, I don't know. Okay, I mean, it's not like electrical charges. So okay, so when the eigenvalues don't repel each other. Okay. However, when I add a vector, I put some charges on the barriers which will repel the eigenvalues. Okay.
And that's how much they move.
Yeah. So the charge on the ith barrier is going to be equal to the projection that v has on the ith eigenvector squared. Okay.
Mm-hmm.
And now the charges are going to repel. Okay. So wait. So in this example, suppose I had a vector v which has projection onto the first, second, and nth eigenvector, and no projection on the third one. Okay. So again, for reasons similar to our argument about naming the eigenvalues, it will be convenient to forget about the eigenvalues which don't move. Okay, so if I add a vector which is orthogonal to the third eigenvector, it's not going to move, so let me just forget about it. Okay. Now, there are some charges on the barriers, and there are some charges that are the eigenvalues, and there's gravity, so things are going to move up the slope. Okay, so this guy is going to get repelled up by this barrier, down by this one, probably down by this one. It's going to get pulled down by gravity. It's going to settle at some point. Okay, and the law of repulsion.
So these charges are what I would call probe charges in physics. They sort of probe the potentials, but they don't repel each other.
Oh, yeah. Okay. Yeah. I mean, I don't know much about physics, but that they don't repel each other.
They don't exist in real life, but we can.
They don't exist in real life. Okay.
Is you thinking of them one at a time, basically?
Right, right.
Uh-huh.
Is this a new type of barrier in computer science?
That was another
I
Adam
don't know.
question.
I mean,
that was another Adam
So
question.
this kind of model was discussed in a book of Sago about orthogonal polynomials. So I'm sure somebody has seen it, but I mean.
Is it a barrier for you?
Now I get it. Now I get it. This is a new type of barrier. Yeah, sure. Okay.
I don't want to ask a question you can just ignore.
I like
no,
it.
That's part of. You have to
Yeah.
figure out which one you should ignore.
Right.
It's a test. Let's go on.
Okay.
There's certain people in this lab you will find out who use their intelligence in strange ways.
I was really following that joke you had about having stock in the movie theater. Actually, I thought it was like real until anyway.
What?
But
We don't even know what
We don't even know what you're talking about.
Oh,
We'll
okay,
know
fine.
about it later, I'm sure.
Okay. So you have these eigenvalues, and the law of repulsion is the repulsion is proportional to the charge on the barrier and inversely proportional to the distance from the barrier. Okay? So what that means is if you get really close to one of these, you're going to get a lot of repulsion. So this is never going to jump across this. And far away it doesn't matter that much. But
And that's why they don't cross.
yeah, that's why they don't cross. And so this is going to go on for a while until you get some equilibrium in which the downward force is equal to the upward force, and this is exactly given by this equation. So this, given a moving charge x, the repulsion is exactly equal to this. This is inversely the distance and proportional to the charge, and gravity is just a 1. Okay. So when this thing is 0, that's where the new eigenvalues are. Okay. So this is a reasonable model for what happens to eigenvalues with interlacing. Okay. Okay, so let me show you a couple of examples to just get you more comfortable with this. The first one, which we've already discussed, is if you just add a multiple of the first eigenvector, you forget about everybody else, and this just shoots out way ahead, and you end up in this situation. Second one, let's say you add a vector which has equal weight on the first two eigenvectors. Well, what happens is that this first eigenvalue is not going to move very far, even though it received a lot of charge, because the second barrier is going to push it down. But then this one is probably going to move forward a lot more because it's being pushed forward by both of these or something like that. The case we're really interested in, because it's related to what happens when you add a random vector, is what happens when you add a vector which has equal projections on all the eigenvectors. Okay, so you add this balanced vector which has equal projection in all these directions. So now you're going to put equal amount of charge on all the barriers, and you expect that something reasonable like this is going to happen. They're just going to drift forward in some sort of steady way. Okay. So I can make this more precise. I can actually look at exactly what happens to the characteristic polynomial under this update. So all these projections are equal to each other. Let me just say they're all equal to 1. It doesn't really matter. And so the characteristic polynomial is simply multiplied by 1 plus the sum of reciprocals of lambda I minus x, which you'll notice is the same thing as just subtracting off the derivative. Okay? Because PA is a product of lambda minus x. Okay.
Why did you replace this VUI?
Because they're all equal, so he didn't.
I'm
because they're
interested in
all
this
1 over
case.
n. So he just.
I mean, 1 over n, 1. It turns out it doesn't really matter. Okay. So if I add a balanced vector, by balanced I mean equal projection of all the eigenvectors, then the characteristic polynomial evolves by subtracting the derivative. Okay. So why would anyone start looking at this? Well, you can consider this. You can go back to what we were doing. If I have a decomposition of the identity, there's some VEV transpose equal to the identity, then for every eigenvector ui of whatever matrix I have at any point, indeed for any unit vector, the sum of projections onto my VE squared is equal to 1. That was just because by construction. And so if I pick a random vector and I look at the expected projection along a particular direction, it's the same, 1 over the number of vectors. Okay. Now, of course, this doesn't mean that there's actually any vector in the collection which simultaneously does this for all our eigenvectors. It's just saying that if I look at any particular direction, the expected projection is about right. But suppose I was in some dreamy situation where this was actually true. Okay, then what would happen? Okay.
Right.
So here's what would happen. So I start with a zero matrix, and I keep track of the characteristic polynomial, which is x to the n initially. And I know that the random vector has the same projection in every direction. So suppose I magically have this balanced vector that actually has this same projection in every eigendirection. Well, I add it, I get some eigenvalue, the characteristic polynomial, I just subtract off the derivative. And then, I do it again. I can, this is generating some sequence of polynomials, and my eigenvalues are just the roots of these polynomials. And so, my intuition was that these things, nothing too wacky should happen, no eigenvalue should be left behind, and these things should sort of drift forward in a steady way. And if I did this for a very, very long time, then maybe they'll end up in a position where the ratio of the largest to the smallest is at most 13. But actually what happens, which is the punchline of this, is that this process generates a classical family of orthogonal polynomials, which are Laguerre polynomials, associated Laguerre polynomials. And everything is known about the roots of these polynomials. So if in particular it's known if I do this for dn steps, I get this, which is exactly what I wanted. So I get that the ratio of largest to smallest is at most d plus or minus 2 squared.
But this, of course, is in this ideal world in which...
Yeah, this is in the ideal world where I can find this balanced vector that has this expected behavior and I can add it. So the proof, the proof is going to be to show that if I'm allowed to use weights, I can actually find vectors that realize this behavior. Okay?
And you don't get the Laguerre polynomials, but you get something else which still has this upper bound.
Yeah. So yeah, the actual polynomials you get are not the Laguerre polynomials, but in some sense the Laguerre polynomials,
like a linear combination. They're some.
Yeah, yeah.
So you would expand them in a basis of the Laguerre polynomials and try to.
Unfortunately, because this is the analysis is totally local, one step at a time analysis, we don't actually know about what kind of coefficients you get at the end.
I see.
But
do you know? The Laguerre formula are also normal in some.
Some weighting, right?
In some way, right?
Right.
So will that be true for yours too?
Okay, so what actually goes on in this is the actual polynomials it generates are not Laguerre polynomials from one orthonormal basis. They're from different. They're not actually orthogonal to each other.
They're coming at each stage. You're getting something.
Right, from a different family of Laguerre polynomials.
So these are the
associated Laguerre
polynomials.
Associated Laguerre
if I
polynomials.
knew how to say your last name,
Yeah.
I would call it that.
So there are these. If you do Laguerre polynomials with weighting x to the alpha e to the minus x, you get something at the parameter of alpha. And what polynomial you get at the alpha nth stage of this is the last polynomial in that family. But anyway, everything is known about those roots of those polynomials. So you get some polynomials whose roots are really good. Okay. And so now what we have to do is show that there are some actual polynomials that realize this behavior. And so now we'll actually do this. And again, we'll do it for 6 and 13. Okay. So here's a broad outline of the proof. So I'm going to have an iterative process again. I'm going to start with all my eigenvalues at 0. And I'm going to control the eigenvalues by two barriers, which are real numbers. And initially, the lower barrier is going to be at minus n. The upper barrier is going to be at n. Okay. I'm going to maintain the invariant that at any stage of the process, my roots are between the barriers. Okay. So initially, this is true. And at every step, I'm going to pick a vector to add from my set, possibly with a weight. This is going to shift the eigenvalues forward in some manner. And simultaneously, I'm going to shift the barriers forward by constants. So I'm going to shift the lower barrier by a third and the upper barrier by 2. These are fixed throughout the process. Okay?
Also, you move them up.
I move them both up. Okay? Now, what does this do? This is the two barriers are doing different things. The first, the lower barrier moving up is tightening a constraint on the eigenvalues. It's saying you better, all the eigenvalues now better be bigger than something that's bigger. Okay? Mm-hmm. And moving the upper barrier is saying, okay, but they better not be too big. Okay? So this is loosening the constraint, but it's saying you better not go off, way out. Right. Okay? So, if I can prove that I can sustain such a process with this, then I can be done. I'll show you on the next slide. Okay? So does everybody understand what's happening in one step? Several things are happening. Some barriers are being moved, some vectors being added, the eigenvalues are moving, and then the thing I'm maintaining is that
the eigenvalues are also drifting.
Yeah, the eigenvalues are drifting, but I'm controlling them by I'm going to assert that I'm going to make sure they're always between these barriers.
But it will be 6 steps before the left barrier hits 0. Right? So
Well, it'll be 3 n steps. Yeah,
steps.
and then at 6 n steps it'll hit, n, which is what I'm about to show you. So suppose I do this, okay? Then this is what happens. I keep shifting these guys. These eigenvalues move forward. After 6 n steps, the lower one is at n and the upper is at 13 n, and that's it. Okay.
I see, and they have drifted because your bounds are not perfect.
Yeah.
They have
drifted further apart. Yeah.
So in the end, your constraints are a little looser
Than they were earlier
to begin with,
Right.
Because you didn't.
Right. I mean,
because there's some error there.
ultimately, if you did this forever, you'd get the ratio 6, because this is moving forward at a rate of 2, and that's moving forward at a rate of a third. But you want to do this in a small number of steps, so you lose a little bit.
Okay.
But you have to trade off like the number of steps versus. Okay.
Good.
Wait, I said one thing I don't. In the beginning,
Why are they at minus n and n?
no. In the beginning, well, you could put them at sort
Yeah.
of 0 and 0, right?
Yeah.
And then you would get But what I don't understand is how does it express that you have a good approximation?
Oh, so if I make sure that my eigenvalues are always between the barriers,
And the barriers haven't drifted too far apart.
then at the
That's
end
whole point.
I have 13 n and n. If I just divide everything by n, then the eigenvalues are between 1 and 13.
And if he had
I
been
see.
able to control the top one a little better,
Mhm.
then he would have gotten a little tighter bounds. We know he can't control it perfectly,
Perfectly.
because there are counterexamples.
Oh, so can I think of it as follows, that you have sort of you start with 0, which has projection 0 in all directions.
Mhm.
And now you randomly add, you in some clever way,
Mhm.
add more and more directions in which you get rid of one of the null spaces.
Yes.
And eventually you get rid of all the null spaces. Actually, you move it a little further.
Yeah. Basically. Yeah.
Would you have been able to prove this about any locations of the barriers at any time?
No.
Or
No.
you really have to?
No,
You can't
so-
just always say, because otherwise you could have initially moved.
Yeah,
the
yeah.
barrier up.
There's some, the limit of, how tightly you can do this is the Laguerre polynomials. You can't do it any better than that. I can show you why that's the case later. Okay. So,
Which is what would have happened with a complete graph or not? What would the Laguerre
not
polynomials have corresponded to?
if you had the sphere, then you could actually just take the vector every time.
Okay.
Adding the balanced vector at every step will give you the Laguerre polynomials.
Okay.
Okay. Maybe not the sphere, but something containing all those vectors. Which,
Right.
yeah. Okay. So, so to prove this, I just need to prove that I can sustain this process. Unfortunately, the way this is set up right now is false. Like, if I just maintain the invariant that my eigenvalues are between two numbers, it's just not a strong enough inductive hypothesis, and it's just not true. Okay. So I'm going to need a better way to measure the quality of eigenvalues of a matrix. Okay. I'm going to need a stronger induction hypothesis, and I'm going to do this with potential functions that are inspired by my physical model, sort of. Okay? So let me worry about the upper barrier first. So I'm interested in making sure the eigenvalues are not too big. So I'm going to define this upper potential function phi superscript u of a to be the trace of ui minus a inverse. Okay? So sum of the reciprocals of the distances of the eigenvalues from u. Okay? So if I know all the eigenvalues are to the left of u, then this function has some nice behavior which reflects how good the eigenvalues are. So this blows up as any of the eigenvalues gets close to u. Okay? So in particular, if I know that this upper potential is bounded, then I know that the largest eigenvalue is bounded away from u. But I actually know a bunch of things. I know that there are no 2 eigenvalues within distance 2, no 3 within distance 3, etc. This actually speaks to the whole distribution of eigenvalues. So there's no.
And how do you know that?
Okay, so if this whole thing is less than 1, then then I can't have 2 of these
Good,
things
good, thanks.
smaller than half, right? Okay. So this says that there's no accumulation of eigenvalues near the upper barrier. Okay. And if you go back to the physical model, this is the total repulsion. If I had no slope, no gravity, I just had one charge barrier here, and I just had these guys sitting over here. So total repulsion. Okay. So the total repulsion is small. I can define the same thing for the lower barrier. It's exactly the same thing. And with these potential functions in hand, I can now do the proof. Okay. So I'm going to maintain the invariant that both the potentials are bounded. Instead of just saying my eigenvalues are between the barriers, I'm going to say that between the barriers and the potentials are bounded. Okay. So initially everything's 0, the barriers are minus n and n, and now it becomes clear why I chose minus n and n, because the initial potentials are now both equal to 1, because I have n eigenvalues at distance n from each barrier. Okay. Okay. So I shouldn't write empty set. I don't know why it says empty set. It should be 0. But yeah. So okay. So in the beginning I have this. Okay. So I'm going to prove the lemma that whenever I have a matrix which has eigenvalues between two barriers and the potentials are both bounded by 1, then I can choose some multiple of some vector in my set that moves the eigenvalues in a way so that when I shift the barriers by a third and 2, then the potentials don't increase. Okay?
And these are the 6n increments that
Yeah.
you're choosing?
Yes.
Okay.
And now if I do the 6n times, then I'm done. Okay? So this is the same thing as before, I just have a stronger invariant now. Okay? So now I just need to prove this lemma. So when you have a matrix with bounded potentials, you can choose some vector to add that preserves both the potentials. Okay? So let me focus on and lets you shift the barriers. Yes. So shifting and adding and keeping the potentials. Okay? Okay. So let me
that you can induct.
so you can keep doing it. Yeah.
Right.
Basically, yeah. So
Iterate,
so, you know, you're looking for a vector to add. I mean, you could try looking for a vector, but really the right question to ask is, given any fixed vector, what is the quantity of it that I can add? Okay? So, I mean, I can add 0 of any vector without hurting the upper barrier, right? So, I mean, the question is, how much of it can I add? Okay? Okay. So, let's answer this question for the upper barrier. So, suppose I have an upper barrier at U. I have a matrix A. I'm interested in adding S times VV transpose, or V is some vector from my set. And I'm interested in incrementing the upper barrier by 2. Okay? So what happens to the potential? Well, the updated potential at U prime of the updated matrix is this thing, trace of U prime I minus A minus S of U transpose inverse. And there's, you know, easy formula from linear algebra which tells me exactly what happens to the trace to the inverse of a matrix under rank 1 updates. This is a Sherman-Morrison formula. So this is another nice thing about the potential. You can exactly explicitly compute what happens to it when you add something. So the new potential is just going to be equal to this. It's going to be equal to the potential at the shifted barrier of the old matrix A plus this quantity. The numerator.
less than 1?
Yeah, I'll show you what it has to be less than. The numerator is some quadratic form in V. Denominator is 1 over S. So S is the scaling factor we're interested in minus some quadratic form in V. Okay? Okay. So what did I want to do? I just want the potential not to increase. So I want this to be at most what it was before. So with this, I can now rearrange this and get exactly what condition is required on S. So it happens to be this. So I can add SVV transpose without increasing the upper potential if 1 by S is at least some quadratic form in V, which I'm going to look at more closely later, but don't.
You did that, what was the phi U, so did the phi U prime of A move or not?
Phi U prime of A?
This one, is that the same as, I mean,
No, that's less than phi U of A.
so that is less than phi U of A.
And then there's this extra
Yes.
positive term in there.
Yes.
So you
which
have
is
to
gonna
actually
bound
control by
S.
how much it went down.
Yes. I mean, because what's happening when you're moving the barrier forward is you're making some space. So the question is, how much can you put in that space for this one vector? Yeah. Okay? Okay, so by rearranging, you get some lower bound on 1 by S, which makes sense. It's an upper bound on S. It's a quadratic form in V, okay? So don't worry too much about these parentheses for now. The point is, it's linear in VV transpose, okay? It's some matrix that depends on A dot VV transpose. That's okay? So I get this. This is how much of a vector I'm allowed to add, okay? A is the current matrix that you have, okay? Okay. UA is some matrix that depends on A. It's this huge thing here, but I'm not gonna like dwell on it right now, okay? So I can repeat the same computation for the lower barrier, and here I get an upper bound on 1 over S, which makes sense because I'm forced to add some amount of a vector, right? So again, this is linear in VV transpose. So this is, I mean, there are several fortunate things that need to happen for this to work. One is you can compute the potentials. The second is that this thing is linear in VV transpose. Okay. So here, I mean, having done these computations, we can go back to what we wanted to show. We wanted to show there is some scaling of some vector that allows us to keep both potentials happy, right? So that amounts to saying there's always a vector where this lower bound on 1 over s is at most the upper bound on 1 over s, because this corresponds to the amount that you can add, and the other one corresponds to the amount that you must add, and if the amount that you must add is less than the amount that you can add, then you can squeeze the scaling factor in between and just do it, okay? No, so it's a little weird. So this corresponds to the upper barrier, but it's a lower bound on 1 over s. So the right thing to do is to look at 1 over s, not s, okay? So, yeah, I mean, yeah, the constraint on the lower thing is on, yeah, okay? So we want to show, so now our problem is reduced to saying there exists a vector for which ua.vv transpose is at most la.vv transpose, okay? And now we use the only property which we knew about these vectors, which is that they form a decomposition identity. So I'm going to prove this by averaging. I'm just going to take the sum of the left-hand side and the sum of the right-hand side, and so that the left-hand side is less. So because it's linear in the outer product, I can just, sum of ua.vv transpose is just ua dot, the sum of these things, and this is the identity. So it's just a trace of this matrix.
Right.
Okay? And this is the point in the proof where I'm shifting to the behavior of this balanced vector. Because by taking the trace, I'm effectively just, if you look at the computation, it's identical to what happens if I had a balanced vector. Okay? So when I transform things in this way, I get the expected behavior. I just get the linear,
It's just the expectation.
Yeah. Okay?
So it's kind of, on average, when you're summing over the v's here, because you pull out that trace, you're fine.
Yes.
Basically.
Yes. Okay. So now let me look at this trace. So this is what I had inside. Okay, so the trace is this thing. Well, the second term here is just the potential of A at the shifted barrier, right? Now shifting the upper barrier forward reduces the potential, so this is at most what it used to be before, which is at most 1 by induction. Okay. This quantity here, the numerator, can be seen as the derivative of the barrier function with respect to the value of the barrier at u prime. So recall that this is the barrier function. This is just trace to the -2. It's just a derivative. Okay. And this thing at the bottom is the difference in potential that I get just by shifting the barrier without changing the matrix. Okay. So this again is just difference between the barrier when it's the potential when it's in u and at u prime. And by convexity, I can lower bound this by the shift in the barrier times the derivative. Okay.
So where do you get? Wait, what is convex? How do you?
So, the way this function goes. Basically, if I use a linear approximation that overestimates how much the barrier goes down.
Good,
okay?
right. That picture you were drawing was a convex function. Good.
So, okay, well now these things cancel, and so I get a bound that doesn't depend on anything. It only depends on the shift in the barrier. So as long as I maintain this induction hypothesis, I get that the trace of UA is upper bounded by 1 over the shift in the upper barrier plus 1. That's it. It doesn't depend on A, it doesn't depend on the barrier or anything. It just depends on the shift. Okay. I can do the same thing for the lower barrier. This is lower bounded by 1 over the shift in delta in the lower barrier minus 1. And this 1 again comes from the induction hypothesis.
But this is like your 1/3 and your 2?
Yeah. And so now I just set 1/3 and 2. And that's it.
I see. So you actually had some flexibility.
Yeah. I guess I could have set, what could I have done? I guess could I have made something, I could have made it 1. Okay.
Yeah.
Anyway, I just wanted to make it clear that this number is bigger than this. Okay.
Right, and you were also telling us that it didn't have to be the same
Yeah.
number. Yeah.
So,
Good.
okay. So I proved this lemma, and so that means you can do this, and that means you can just do this, and that's it.
That also imply that you were always between potential was
Yes. Yeah. So you have to take some care to make sure nothing jumps across, but basically that's because these inequalities hold as you vary the eigenvalues continuously. So if it jumped, then something would blow up. So basically, it doesn't jump over the barriers. So yeah, you have to take care of that. But it comes for free. So that finishes the proof of the theorem. And if you do everything carefully, then after dn steps, you actually get this quantity, which is not actually the Ramanujan ratio. It's a little better. So it's worse for d less than the golden ratio and better for d greater than the golden ratio. But you get this quantity, which comes from the roots of the Laguerre polynomials. Okay. So actually the exact origin of it is not the same as the origin of those numbers for the Ramanujan graphs, but it just happens to be like better than it for, anything greater than the golden ratio, so for integers. Okay? Okay, so I mean that finishes the proof of the theorem. I mean there are some open questions left by this. So can you get rid of the factor of 2? If you do this to the complete graph, can you get unweighted graphs? So right now it's really slow. It's like n to the 4th. Can you do it?
Why is it an algorithm? Because you just said the exist one, right? Because you showed that the sum is smaller than...
But you can do it.
So it's an algorithm because you can just brute force look at all the vectors. So the way you check if a vector is good is by looking at like this matrix, right? So you can compute this. So the problem is this involves inverting matrices, so it takes n cubed time. So in every step you have to do some matrix inversions to compute this.
And then try out all...
Then just try all the vectors, yeah.
Wait, there's all the vectors? I mean, I don't understand.
If it's a finite graph, then...
The number of vectors is infinite, no? Because
These are the...
Oh, they come from the edges.
the vectors always just unit on one.
Yes.
Yeah. So that's just... You have to try the number of edges
Yeah,
times.
so it's dmn cubed. Or something like
M's
that.
in there.
There's an m in there, actually. Yeah.
There's an M in his bound.
So maybe it's n to the 5th, I guess.
Something like that.
But yeah, so I guess it's a pretty brute force algorithm. So it's kind of slow. So is there like a way to do it better? And then the main question suggested by this is this thing called the Caddis-Singer conjecture, which is some old conjecture in various areas of math, which basically comes down to the question: if all my vectors have bounded norm by a constant, like 0.01, then I would like to show I can partition the set into 2 sets, each of which are sparsifiers for the original set. So I have some decompensating identity. I want to break it into 2 things that have constant condition number. Without weights.
Oh, without
weights. Yeah, without weights.
I see, because you
Yeah.
did it with one.
Yeah.
You did it with a weighted one.
Right. So that's so this is a pretty old conjecture, and I mean we were able to get...
Why does one want to be able to do that?
I don't know. It comes from quantum mechanics. It has something to do with like C-star algebras. It's some like really old...
Okay. Well, yeah,
I mean, there's no really...
makes sense.
There's no... I guess I just want to do it because it's a simple property about vectors, but presumably I think other people want to do it for various other reasons.
Okay.
It has something to do with frames as well. So we were not able to prove this. I mean, we're trying, but we were able to recover like the best known results about it using this technique, much shorter way. And I guess another question, which is, probably the most useful one out of all of these, is like, can you do this quickly for if you know your graph like is like a real graph, like if it's like a power law graph or something like that. Like, can you do this like faster? I mean, who knows what real graphs look like? Fine, but if you know it's from like a particular family of graphs which people actually use, like for scientific computing, well, those are mostly sparse anyway. But suppose it comes from something, then do you have to do all this stuff? I mean, can you?
Right. If I'm trying to get
Yeah.
some approximation to the web,
Right.
which preserves clusters or whatever,
Yeah.
can I do it fast?
Yeah. Okay, so yeah, that's it. Any questions?
I think like if you had if you had a social network, right?
Okay.
You wanted to know sort of like how often 2 people use the same cell phone, or how often they do something with the network, and you wanted to run an experiment.
2 people use the same cell
I
phone?
mean, same carrier.
Oh, okay, fine.
Same carrier.
Okay.
All the friends use the same carrier, within different cliques or something like that, in different groups.
Okay.
Instead of doing an experiment where you just did it on all the edges in the graph, which are very expensive, or random
Right.
edges, you could do it on the edges that your algorithm proposes. But the question I have is, your algorithm, can you make it so that if you randomize the algorithm so that the expected value of the adjacency graph equals the
Right.
graph?
So in this previous algorithm with the log n, that does hold.
That just does hold
But
by itself,
I don't think there's a way to get around the log n. I mean, if you
want it for that.
So unfortunately, the constant in that algorithm is 4 log n. So I don't know if that makes it any better for real life, but it's not like some huge horrible thing. So, but it's still log n.
And you're not aware of any particular instances where your graphs that you're generating are really
like structured?
Imbalanced. No, very imbalanced, like whereas the starting graph didn't seem to be that. So a regular graph that you start with, and you end up with a graph which is sparsified,
but the combinatorial degree is really
combinatorial degree
messed
is very
up.
lopsided.
I mean, I can think of some vague techniques for trying to avoid that. I mean, so the nice thing about this process is it's like very tweakable. Like each step you can do something different if you like. So, but yeah, I cannot think of a graph which would force that, certainly.
Great, thank you.
Okay.